Hello everyone and welcome to the Data Journey YouTube channel. Here in this video we are going to learn how K-means algorithm works and how it can be used to do clustering. So as usual, let's go to the drawing board to understand how this algorithm works in theory, and then we'll implement it in Python using scikit-learn. So here in the drawing board I'm going to draw two axes, basically a 2D plot, just with some random data points for us to understand how the algorithm works. So I'm going to go here, I'm going to draw these data points, so some data points here, then I'm going to draw here as well some more data points, and I'm also going to put one data point here. Okay, very cool. I'm going to call these two variables, so this is something that everyone understands, age and salary. So here in these two variables, what we see is that we have two big groups of people, or in this case, if we specify that each of these data points is a person, we would say that these people are young people with a high salary, and these are older people with a lower salary. Okay, let's disregard now what are the values here and what is the range of the axis for now. Okay, just for abstraction, just for the thought process. And we also have this person here, which is a younger person with a lower salary. So a K-means algorithm aims to create a clustering algorithm that will tell you that these groups exist in some way. And it's in the name of the algorithm. So K-means really is just trying to find a certain K, or to have a certain K that will fit what we have in the underlying data points, in this structure that we have in the data points. And the first hyperparameter that you need to define in K-means is exactly the K, because the algorithm doesn't find it by itself. There's only rules of thumb to choose what's the optimal K, and there's no set in stone rule that you can use. But there are certain things that we can do, as we will see. One of the most famous ones is the elbow method, that lets you understand at which point adding a new cluster doesn't bring you that much value, and that's normally where you choose the K. But K-means, let's imagine that our K is 2, would start in this way. Let's represent these points, or in this case another different shape, as our centroids. Okay, and I'm going to put them randomly here. This is exactly how K-means work. Okay, I'm going to put this centroid in blue. Now the first step of K-means is to calculate the distances between every data point and the centroid. So we could say that probably these data points are nearer to this one. Okay, so I'm going to highlight them in orange. These ones as well. So let's imagine that this is happening. So all these data points are nearer to this centroid right here. And I would say that these three probably I can put them in blue, saying that they are nearer, these ones are nearer to the blue centroid that I have right here, to the blue element of the K. Okay, so to recap, we started with a K equals to 2, and we randomly throw our centroids to the plane, to the 2-dimensional plane. Now these ones are, I would say that these ones are near the blue, so I'm going to highlight them in blue, and I'm going to say that probably these ones are nearer the orange one. Okay, there you go. So of course we would now be saying that these data points, oops, I missed one here, that these data points are represented by this centroid right here, and the blue data points are represented by this one right here. Do you think that this is a good clustering solution? Doesn't seem so, right? So what we would like to do now is to in some way recalibrate these centroids so that they match the underlying structure of the data. And this is where the magic starts to happen. So in the next iteration, we will drag the centroids to the center of the data points where belong to that centroid. Just know that belonging to that centroid means that the distance between the data point and the centroid is the minimum when you compare with all the other centroids. So if we had 10 centroids, this data point would be allocated to the nearest centroid of those 10. Okay, so that's the choice. And how can we do that? Basically, we just move the centroids to the average of all the data points that we have allocated to that centroid. As simple as that. That will produce a kind of a vector that will move the centroid to a certain direction. And here what we can assume is that, for example, we have here a lot of data points. So we have here 1, 2, 3, 4, 5, 6, 7, 8, I would say. And here we have 4. So it's natural that the centroid would be more near these data points than these ones, because the average of these orange data points would go somewhere around here. If you imagine we have, for example, a line here, and some data points are pulling the line, and the data points are pulling the line towards them, we would say that we have more data points here, so they have more strength, right? So that would be the case. The centroid would be somewhere, I would say, along this line, probably here. That's very interesting. Now the same happens with the blue centroid. We have more data points here on this side than on this side, and that's exactly what happens. But now it isn't on a straight line, because there's this bad boy right here that is also pulling with some strength towards its side. So the new centroid would not go in this line, it would go a bit below, probably I would say here. Okay, so these are the new centroids. I hope this makes sense. So what we've done is just move our centroids. So this centroid, the blue one, is located on this direction, and the orange one is located from this direction to this direction. Okay, so it came from the original position to a new position. Now, is our solution finished? Of course not. What we will do is basically just go here. I'm going to change the points again and return them to the original state, and we repeat the idea. So we now calculate the distance between the data points and the new centroids that were recalibrated again, okay? And by doing that, we'll know that all these data points will belong to the blue, and all these data points will belong to the orange. So simple as that. And now, as you can see, we can move the centroids again to the center of the data points. Now, this one will unambiguously come here, and it will be the centroid that represents all these data points, but this one will not be here. It will be a bit below, probably here, because of the outlier. So this is a very important on K-means, because outliers have a very, very high impact on this type of clustering, because they will also apply some force, and the force will be the same as the data points that we have in a specific cluster. In self-organizing maps, that will be a bit different, and that's why they are a bit more robust to these types of outliers. We'll see that also in future videos. But here, just know that when you have outliers, as we will see when we do our implementation, the outliers will pull the centroids apart, and that's very important that you understand, because normally you would like to remove outliers before applying a K-means solution, because you don't want to have a centroid with 2 or 3 examples or 2 or 3 observations. That is something that doesn't bring much value, okay? Okay, cool. So we have here a solution, a K-means solution, and this seems to represent the data points, the underlying data points, a bit better than the random that we had, right? If we had a new centroid, let's imagine the green, I would bet that that new centroid would go here to this data point, and we would have 3 clusters, okay? So something like this, and this one would be allocated to 3. Now, again, doesn't mean that you really want to have a cluster with one individual or one example. It depends on the use case that you are doing, but it's important that you understand that these outliers have an impact. Now, how do we find k? We started with k equals 2. Is that the optimum k to use? Well, we don't know what's the optimum k to use, but we can have a rule of thumb to define it. Now, one of the things that we do and we can do to classify this solution is just calculate, and let me put that here in, I would say, let me choose another color, probably purple. So the solution is classified by the distance of every data point to its centroid. So we can pick up all these lines, right, and just do this. So imagine that we would have purple lines for every data point to the centroid, and here the same, and here the same, right? Now these purple lines, the sum of these purple lines is the amount of lost variance. So is how much we are sacrificing to consider the cluster, right, instead of considering the individual data points. Makes sense, because if we are trying to categorize this data, we will classify. Let's imagine that this individual right here is called John. We would not be naming John, we would name the high salary younger people. So we would lose some information because there's a variance in this data set, right? John is actually the person that earns the most in this data set, and we would consider that on average John is earning a bit less because of the centroid. So how we can choose k is that when we increment k, so if I keep adding centroids right here, these purple lines would keep getting smaller, and the variance of course would keep getting smaller up until the point where I have a centroid for each individual. That means that I have the original solution and the variance is 0 because the number of centroids is equal to the number of individuals or number of observations. If that happens, that isn't a clustering solution, it's not that meaningful, but the variance is indeed 0 because there's no distance between the data point and the centroid. So if we start to increment centroids, there's a certain point where adding a new centroid won't reduce these distances too much. When that happens, probably it's a good place to stop k because adding a new cluster only adds complexity and doesn't split that much of the data points. For example, here, what we would see is that, let me just remove the purple lines. If I add k equals 4, and let me add here another purple centroid, which are represented in purple, is that we would probably have a new cluster here, and these two data points would be allocated to this centroid right now. So we would kind of be splitting the young, high salary people into two groups that it doesn't seem to make sense. Well, it depends on the application, but at least in theory, it doesn't bring that much value. This would happen on k equals 4, and you would see just a small bump on k3, on k equals 3 to k equals 4 in terms of the variance. I hope this makes sense, and I hope that you've understood this explanation of k-means. Now let's go to our notebook and implement this in Python. So for this one, I'm going to need sklearn.cluster import k-means. Okay, I'm also going to need sklearn.preprocessing import standard scalar. So I'll explain why we need to standardize the data in a bit. I'll need pandas spd, of course. I'll also want to use matplotlib.pyplot splt, and also I want Seaborn to do some interpretation of the clusters. Now the data that I'll be using is the data of companies, so I'll use some data from the Standard & Poor's 500. So what I'm going to do is just pick up all the companies in the Standard & Poor's, which is an index of the largest companies or by market cap in the US, and I'll check which companies I can group together based on their financial data. I know that it's not probably the sexiest example, but even so, it's a cool example if you want to also understand a bit of how this part of finance works. So I'm going to use this data here. Alright, so I'm going to do financial data is equal to pd.read.csv. I've uploaded the file to Google Colab. I'll also give a link for you to have access to the same file. And I'm going to copy this folder or this file path and put it here. So let's just see the financial data. I'll see the top 5 rows. So here we have company name, the symbol of the stock that is trading on the stock market, the sector of the company, the price of the stock, the price to earnings, which is dividing the price by the amount of earnings the company has, dividend yield, which is how much the company pays paired with the price of the stock, how many earnings per each share they have, so how much money they make for each share that they have, because the company is split into shares. Don't need to worry about this. The price to sales, which is a metric of valuation, and the price to book as well. Okay, so what we'll do is just pick up this financial data, some of the variables, particularly the ones that are comparable. For example, price is not comparable because it depends on the number of shares. This is something important, which is a company with a share price of $1,000 doesn't mean that it's more expensive than a company that costs $10. It doesn't work like that, because imagine if you have a single share of $1,000 in a company, that's the price of the whole company. But if you have 10 million shares at $10, then that company has probably a different market capitalization as well. So price is not comparable. What's comparable is, for example, price to earnings, dividend yields, earnings per share. Everything that is kind of a ratio can be used for comparison, and that's what we are going to do here instead of absolute numbers. So I'm going to choose the following features. So features for clustering will be the following. So price, earnings, then dividend yield, earnings per share, price to book, and price to sales. So these will be my features that I'll use for fitting a clustering solution here. Then I'm going to do clustering base here would be equal to financial data features for clustering. Okay, cool. Here I'm going to remove the nans because we need to remove some nulls. There aren't that many, and honestly we don't want to go too deep into them. So what I'm going to do is clustering base is equal to clustering base dot lock, and just remove everything, or price to earnings dot isNA, just removing the nans from the rows that have this column with null. And also I think the price to book also has some NAs, so let's run this one. Okay, and now we just, I think there are 10 rows or something like that. Let's just check for our consciousness how many NAs we have. We have no nulls because you can't fit any solution here in scikit-learn with nulls. It will immediately trigger a warning. And now we'll need to scale our data. Why do we need to scale our data? Let me go back to the drawing board. Well, mostly there's a rule of thumb, which is everything or every algorithm that's based on distances, particularly relying on Euclidean distances and Manhattan distances. I think cosine is not that affected because it's an angle, but even so, I think out of I think it's always better. Everything that's relying on distances needs standardization. An example of something that isn't affected by distances is, for example, tree-based models. They aren't affected by distances, so they don't really need standardization. But everything that kind of relies on distances in some way needs to have standardization. So you need to have the features in the same scale. And here, for example, age and salary have completely different ranges, so at least I hope so. If they are in the same range, there's a problem. So you have salaries going to the 0 until the millions, and age normally only goes until the 100, max 120, 100. I don't know what's the maximum age that someone got to, probably 125 or something like that. So those are different ranges. What would happen if you didn't standardize is that salary would basically define your clustering solution. You would be basically crushing everything into a single dimension because age wouldn't have that much variability, so you would just have variability on the salary. And if you do that, probably these two clusters would be together. That's something you would probably not want. So you'd have a certain dimension having an impact, or a higher impact than the other ones, something that wasn't proportionate, unless you want to, but I don't think that that's something that you would like, to the solution. So we need to standardize this data. What I'm going to do is scalar is equal to standard scalar, and I'm going to use the standard scalar because normally works well, and scale data is equal to scalar.fit transform clustering base. That's it. Now we would have here, if we go here, we will have an array of scaled data, and that's something that we would want. This represents the original features. Now we don't want to do a single case solution. We want to check our solution for several cases. That means that we need to fit several different K-means algorithms, and that's what we are going to do here. So what I'm going to start is with a plot that will get me the distances between each data point and the centroid for every case solution. So for k equals 1, I'll have some purple lines. For k equals 2, I'll have different purple lines that, remember, they are shorter, the purple lines, because there's a new centroid. It's like when you think that you have to walk to a certain bus stop. If someone puts a new bus stop between your street and the bus stop that you have to walk to, you will have to walk less distance. So if you think about this analogy, it works here. If there's a new centroid, it's a new bus stop, so most data points have to walk less to catch the bus than they had before, because they had a bus stop that was more far away, and by bus stop I mean centroid. Okay, hope this analogy works. And here for k in range 1 to 50, what we will do is just a k-means solution is equal to k-means, and here n clusters is equal to k. I'm going to use random state equals to 0 just so that the centroids start on the same place, and you can also use this to have similar results. And then I'm going to fit this solution, doing everything at the same time. I could define the object. I'm also even going to do that. So kmeans.fit scale data, because you are probably more used to this way of work in scikit-learn. You define the object and then you fit it on the data, right? So going to do this and not jump ahead. And now what I'll want to do is the dispersion. I'm going to append KMeans dot inertia. I don't know why they call it inertia. I really don't like the name. I would prefer, I don't know, another one, but whatever. Let's call it inertia. So inertia is the distance between every data point and the centroid that they have been allocated to in the end of the solution. Okay? So I think that in the original KMeans version, let me see here, the default is that the algorithm runs for 300 iterations. So it tries to move the centroids 300 iterations. The only thing that we are changing with our arguments is the n clusters, the random state as well, but really changing is the n clusters. So first we'll run this for 1 centroid, then 2 centroids, then 3 centroids, then 4 centroids. We'll collect the inertia, which is the dispersion basically, and we'll append it to this list so that we can see the evolution as well of how the variance changes. So let's run this one and just wait a bit. I think that the default value of n init is changing. That's okay. Don't worry, because the algorithm is running. So now let me go to the materials. I think it's easy just to pick up this plot of the inertia plot. This is just a simple scatter plot. I don't need to write it by hand. And let's see it. Wow, now very cool. So let me explain this plot. This is what we normally call the elbow curve, and is something that we use as a rule of thumb to define the number of clusters. So as you can see here, we have the dispersion, or inertia as you want to call, which is the distance between every data point and its centroid, the total distance. If you think about the purple lines, it's the same as if you add all the purple lines that we saw there, okay? Then what we have is the number of clusters. So for each number of clusters, for each number of k, for each different k, we would have, of course, a different inertia, different dispersion. As soon as you have more k's, you have more bus stops, and you have to walk less to the centroid. So in that case, the sum distance is always changing. Now notice that it kind of hits a plateau. It kind of does this big ramp. It does this big ramp, then the slope starts to slow down, and you start to have a less steep descent. When that happens, that's a good point to choose a k, because adding a new cluster will only add complexity. This is very interpretative. There's other things such as the silhouette coefficient that I'll leave in the resources for you to see that also are good rules of thumb to choose k, but there's no mathematical proven way to be the best. It depends on the use case, and it always depends on the interpretation of the clusters depending what you want to do. That's very, very important. Interpretation is key on KMeans. And in most unsupervised algorithms as well. That's why they are so used in things or in problems where you require a lot of domain expertise. Alright, so I think I'm going to choose something here between probably the 9 clusters. So around these data points, although I still have a curve, I could choose, for example, I don't know, 30, but that would be a bit cumbersome to analyze. And you'll see that this solution is also not the optimal because of the outliers that we have. That's also interesting. So let's now fit just a solution with 9 clusters. So what you can do is just go here, pick up this line of code, this KMeans, put it here, and instead of n clusters k, now you can use n clusters 9, and I'm going to call this n KMeans 9 just to differentiate. And then KMeans 9.fit to the scale data, and now I can do to my clustering base. I'll add the clustering KMeans. I'll add KMeans.predict of the scale data. I could also do a fit predict here as you want. You can use the methods from scikit-learn as you wish. I'm just doing this just to keep coherence with what we've done before, and so that people that aren't really that familiar with scikit-learn are able to have at least something coherent here. And now I'll want to add this to the scale df as well. So I'll create a data frame for the scale df because I'll want a column with the clustering with the cluster KMeans just for something that I'll do next, where I want to have an interpretation via a heat map. To do that, it's better to use, and here columns would be financial data, clustering, features for clustering dot columns. Okay, here it's not scale df, of course it's scale data, and already Colab is telling me that this variable doesn't exist. This is just because I don't want to have this. I don't want to change the columns to cluster KMeans. Don't need to worry about it. This is just to create the scale df. And then for index, I'll want to use the index from the clustering base because we've removed some values that have the nans. So this would be it. And now I can add to the cluster KMeans. I can add the clustering based KMeans. I can even add this one directly. Okay, this is exactly the same. I'm just predicting what's the cluster for the clustering base original variables, because when we do interpretation by means, we would like to have the original variables, but then in a heat map, as I'll applying color scales, I'll want to see them in the scaled version. So let's run this one. I hope everything is correct. It seems so. Cool. Let me do something. I'm going to do the first interpretation of these K-means. And how can we interpret clusters? Just look at the averages, right? That's the most basic interpretation that we can do. So group by, and then I'll do a mean. And we have here about 50 clusters. Why is that? Or 49 clusters. Why is that? Well, because I forgot here of you doing k-means 9. I'm using the last implementation. So that's also interesting. Basically an error. It's also cool that I make these mistakes from time to time, because that's super common also when you are coding. Okay, now I think we'll have 9 clusters. There you go. Now let's interpret these clusters. So one of the things that I completely notice is that we have here a cluster that has a very high price to book. So these are super pricey stocks. What means price to book is that they are very expensive regarding the assets of the company. Don't worry about this concept. Just know that this is something that translates into very expensive companies, as well as the price to sales. For example, we have this cluster where you are paying $13 for every dollar of revenue of the company. It's very expensive. Let's see other interesting things. So we have here a group of companies that have a very, very high dividend yield. This is normally characteristic of utility companies, real estate companies, companies that are in a more traditional space. They don't grow that much, so what they do is that they distribute a lot of money for the shareholders via dividend. On the other hand, when you have low dividend yields, that normally means technological companies. And I bet that this cluster 2 is that because high price to earnings, so they don't earn that much money, but they are very, very expensive as companies. It means that the shareholders are really betting, and the stock market is really betting that this company will grow a lot in the future, because you are paying a lot for their current earnings. So the difference between price to earnings and price to sales is just in terms of accounting. Don't need to worry about it. Just know that when they are high, you are paying more for what the company is making in sales and is making after paying all the expenses. So just keep that in mind. Now, earnings per share is also interesting. These companies, this one on cluster 5, they seem to do a lot of money for each share that they have. It would be interesting to investigate it. Now, another thing that I like to do when I interpret clusters is not only looking at the difference in the means, also looking at the heat map. Let me go to the notebook here that I'll also give you in the end, and just run this heat map here. I already have the code, don't need to write it again. And this is the same information that we have above, but it's with a standardized version. And for color scaling, it's better because you immediately see like what are the variables that are impacting a lot of the clusters. Now, when you see these big jumps in a k-means algorithm, that means that probably you have to investigate if these are outliers or not. Because I bet that these 5, 2, and 1 they don't have that many companies, they don't have that many data points. And let's confirm that by doing here, I don't need a group by, I can do scale df dot cluster k-means dot size. Okay, so which ones I was saying? I can't apply size, I think. No, I can apply value counts, of course, makes sense. Okay, cool. So remember, 1, 2, and 5. 1, 2, and 5. See? So it would be good to check if these are really outliers or not, and if you need to do some outlier treatment to these data points to make this make sense. Okay? Very important when you see these clusters, don't jump into conclusions right away, because normally when you have these big stretches in the clustering solution, you have outliers in there, and you may need to treat them before going into the k-means solution. Now, as you can see, k-means is really sensitive to these types of outliers. For finishing this video, let's just analyze some of the companies in some of the clusters and see if our assumptions are correct. So what I'm going to do is go here, clustering base.lock, and I'm going to choose cluster KMeans. I would like to see these ones that have a very, very high price to book. Oh, by the way, I would like to select just the index from this. So index of cluster, index of companies. I'll want to go with this index to the original data frame, because here I don't have the name of the company. So now financial data.lock or ilock, oops, index companies. Okay, just want to see the name of the company. Okay, interesting. So as you can see, you have here a very high price to book. This is probably something having to do with the financials of the company. I bet that they have like very, very high liabilities and very few assets. So the book value is probably very low, abnormally low, and it doesn't represent the reality of the company. So that's interesting because these are really outliers. Now, let's see, for example, cluster 2. I would like to see, so cluster 2, as I was interpreting it, we have a very high price to earnings. These are very expensive companies, very low dividend yield, the lowest of all clusters if you compare them. Also, very low earnings per share. So I bet that these are technological companies. Let's see. And there you go. Yep, most of them. You also have here other types of companies, but most of them are, for example, Salesforce, Netflix, Amazon. So companies where investors are betting on a lot of growth. I don't remember what was the year of this data set, but it's not like this year, and I don't think the last 2 or 3 years. I would say that probably this is like 4 years or 5 years ago. But it's very interesting because they are indeed technological companies. And now, let me check, for example, let's see these companies, the 8 that have a very, very high dividend yield. I'm betting that these are companies. I've done this before and I also had these assumptions, so I'm just confirming it. So I know that this will be financial, utilities, telecommunication, energy. So as you can see, very, very traditional businesses. And you can see them here as well because they normally distribute a high dividend to the shareholders. And that's why they are being clustered together mostly. They also have other things that are important. For example, a low price to earnings. They are not that pricey in terms of the share price. They have a low earnings per share. Have a kind of average price to book and price to sales. These are the most boring companies, if you would like to give a name to the cluster. Okay, so just have a go and interpret the other clusters and see if you can get also some conclusion. Alright, so in this video we've learned how to work with KMeans, understand how KMeans work, and also learn how to fit it here in scikit-learn. Important things: KMeans have one important hyperparameter. It's in the name, K, which is the number of clusters. Then we have to understand that we need to standardize the data so that we don't overweight one of the variables in the solution. And also we've understand that outliers have a very, very high impact on KMeans as well. Finally, you can use from sklearn.cluster KMeans. That's something that you can use right off the bat from scikit-learn and implement this for your projects. I hope you've liked this video. If this was a bit alien to you, all this Python code, feel free to join my Python for Absolute Beginners course on Udemy. Links are in the description and I would love to have you as a student on my course. Also, subscribe to the channel and hit the bell to get all the notifications when I upload new videos about data topics. So I'll keep uploading more things about data. You also have other videos on the unsupervised learning series on this playlist. Check them out if you would like. Thank you so much for watching until the end, and good luck on your data journey.